All right. Welcome to my exam 3 practice review. I accidentally started without the mic, but let's go ahead and get started here. Which of the following is a weak acid? You should be familiar with the 6 strong acids. So nitric acid, which is HNO3, H2SO4, perchloric acid, which is HClO4, and then you have HBr, HI, and then HCl. These are the 6 strong acids that you really need to know for this class. So if it's not on this list, it is weak. If you do not see it on this list, it's weak. And going by that logic, that means D is my only one. So now you might be tempted to think like, oh, HF is strong because like it's also a halogen. But no, HF is the only halogen, the only halogen acid that's really not strong. I guess if you go out into the bottom. Anyways, HF is not strong. It's really electronegative. It holds on to its hydrogen. Anyways. Which of the following is a weak base? So this wants you to look at the properties of ions as they relate like conjugate acids and conjugate bases. So what I've been telling people in my sessions that if it's strong, like if it comes from a strong acid or a strong base, its conjugate will be neutral. Similarly, if it comes from a weak acid or a base, its conjugate is also weak. So, for example, this problem wants us to look at which of the following is a weak base. So what you want to do is 1, divide into ions, and then 2, determine where it came from. So, for example, like if I have like a chloride anion, I know that had to come from HCl. Typically, if it's an anion, it's going to come from, or it's going to be the conjugate base of some acid. And if it's like a cation, like Ca2 positive, it's going to be the conjugate acid, or it's just going to be the conjugate of a base. So like Ca2 positive comes from calcium hydroxide. So in this case, you want to look at their ions. So for example, NH4 positive and then Cl minus. So what I'd want to look here for is that NH4 is a weird one because it's sort of not like these over here. NH4 is the acidic or conjugate acid of NH3. Remember, this is a weak base, and it's why something like this, or the Bronsted-Lowry definition of an acid or a base, is what allows something like this to be considered a base, right? Because it accepts hydrogen to become this ammonium on the left. Obviously, you know this has to be the acidic form because I can't have something like this for nitrogen, or those are H's. I can't have something like that. So I know that this has to be the acidic form. And so because this is a weak base, that means that this is a weak acid. Remember, like I said, if it's a weak acid or a base, it's going to have a weak conjugate. So this solution is acidic, so I can automatically cancel that one out. So, because this chloride right here is going to be neutral because it comes from hydrochloric acid. So now I want to look at the next one. So sodium cyanide comes from Na positive and Cn minus. And this sodium is going to be the conjugate of sodium hydroxide, and this is going to come from hydrocyanic acid. And look, this isn't on my list of strong, so that means that this is weak. So that means this is a weak base. And that because this sodium hydroxide is strong, that means sodium's neutral. So I can go ahead and circle B, but I want to go ahead and just confirm the other ones. This potassium comes from potassium hydroxide, so it's neutral. And this bromide comes from hydrobromic acid, HBr, and that's strong. So I know that this whole molecule is neutral, right? Because this potassium comes from potassium hydroxide, the bromide comes from hydrobromic acid, and I know that these are both strong, respectively, so I know that their ions have to be neutral. All right, so X. And then for the last one, same thing as before, we already determined that sodium is something that's neutral. And so if I look at this, this nitrate comes from HNO3, so nitric acid. And if I look, that's on my list of strong, so I know that nitrate has to be neutral, so I know that is also incorrect. All right. Next problem, calculate the concentration of OH in a solution that has a pH of 4.2. I'm actually going to pause right here because I'd actually like to go over the equation that you really need to know for this class. Like without a doubt, like you should be able to whip these out on the test. So this covers 16, well, I guess both of the chapters, so there should be roughly 12. And I just like to have them all out in front of me. And I promise it seems really hard, but it's not. So we have Kw, which is that auto-ionization of water. So the auto-ionization of water is essentially water reacting with itself in solution. So this is always happening. So it's just mini acid-base reactions that are happening in water because it's amphoteric. Remember, amphoteric means it can be an acid or a base. So I just write A or B. So we have this auto-ionization of water equaling 1.0 times 10 to the negative 14 at 25 degrees Celsius. This number will change with temperature, but if you see 25 degrees Celsius, I know I can use the 1.0. And this will equal the concentration of hydroxide times the concentration of hydronium. Let me actually make this a little bit bigger. Kw is also equal to Ka times Kb for a conjugate acid-base pair. Oh, that is horrendously large. So this is for a conjugate acid-base pair. I can't use this for something like HNO3 plus NaOH. And, well, first of all, they're not even going to have Ks or Kbs because they're really strong. So this Ka and Kb is for conjugate acid-base pairs, like point blank. All right. So what else we have? We end up having, we have these Kas and these Kbs, which are the tendency to ionize, right? So Ka is equal to hydronium ion concentration times conjugate base concentration over that over that acid, which is weak, right? So I'll just write out Kb. Kb is sort of the opposite. It's concentration of hydroxide times the concentration of that acid over A minus. And if you think of this in terms of equilibrium, products over reactants, something that has a high product concentration is going to have a large Ka. And when it comes to acids and bases, these high product concentrations like H3O and A minus indicate the strength of an acid, because a strong acid is going to ionize completely, right? So strong acid, I'll try base as well, equals complete ionization. Meaning that in the solution, let's say if I have NaOH in that beaker, I'm going to have, well, it's aqueous. I'm going to end up having OH. Well, hold on. Let me see where I'm at. All right, 1 second. All right, sorry about the interruption. I was getting a phone call. So, as I was saying, let's say I have like sodium hydroxide. In this solution, because it's so strong, I will not have any like complete like sodium hydroxides, right? It's all going to be ionized, which would be like OH negative plus Na. So like same thing with the acid. So if I had like nitric acid, I'm not going to find any nitric acid whole in that solution. I'm going to end up with like nitrate, and then I'm also going to end up with like H3O positive. Something important to note is that this hydrogen right here is never just going to be free in solution. It's always going to end up being bound to water, right? Because you don't just have free hydrogen ions floating around. So strong acids base ionize completely. So a weak acid or a base will not. So weak equals does not ionize completely. So the way we can measure their strength, right, is using those Kas and those Kbs. So a stronger weak acid or a stronger acid is going to ionize more readily than a weaker acid. That makes sense. I'm sorry. So a larger Ka will denote the strength. So increased Ka equals increased strength. And something we can note or we can derive based off of the relationship between 2 and 3, these equations. If my Ka increases, and I know that this Kw is a constant, right? I know that if, let's say, my Ka is larger, that means my Kb has to be stronger, which leads me into my next point. The increased strength of an acid, which, I mean, we sort of touched on earlier with the whole relationship between, strong acid base equals a conjugate or a neutral conjugate, the increased strength of that acid, I'm just going acid strength equals decreased strength of the base. Right? So, like I said, increased Ka is going to be equal to a decreased Kb for that conjugate base. Similarly, if I have an increased base or a stronger base, I'm going to have a weaker conjugate acid. And that's why when you have like NaOH, this is so strong that its conjugate is neutral. This is so strong that its conjugate is neutral. It has no tendency to take electron or take hydrogens, right? So moving on, we have, let's see, we have the relationship between pH and pOH. So the pH of a solution plus the pOH will be equal to 14. So that's to say, like, if I have a pH of 6, I have a pOH of 8. And while we're at it, 14 is also going to be equal to pKa plus pKb for a conjugate acid-base pair. And this 14 sort of comes from that to the negative 14 that we have up here for that Kw. So I wouldn't dwell too heavily on that. But let's see, we can also define pH equaling negative log concentration of H3O positive. So whenever you see P, just know that means negative log. So P is essentially saying negative log. It's like pKa is negative log of a Ka. So we also can have, like, let's say a problem gives us the pH and it wants us to find the hydronium ion concentration. Well, hydronium ion concentration will be equal to the pH. Well, it's going to be equal to 10 raised to negative pH. Similarly, I can find the pOH of solution, which is going to be negative log of hydroxide concentration. And same thing as before, hydroxide concentration will be equal to 10 raised to the negative pOH. And so then my last two equations that I think are really important to know for this class, sorry, let me erase this over here, is going to be the Henderson-Hasselbalch equations for both pOH and pH based. So these are for buffer solutions that contain a conjugate acid and a conjugate base. So I'll delve into conjugate bases in just a second, but so essentially this is pH equals pKa, so the negative log of the Ka value, plus log of base concentration over acid concentration. And same thing over here, pH equals pKb plus log now of acid concentration over base concentration. And so these are going to be for buffer solutions when I contain a conjugate acid and a conjugate base. So I'd like to just remind you guys all what a conjugate acid and a conjugate base is. So these are two substances that differ by one hydrogen. One hydrogen. I'm going to say it again, one hydrogen. So something like OH minus and hydroxide and hydronium are not a conjugate acid-base pair because they differ by two hydrogens. So an example of a conjugate acid-base pair has to be something like Cl minus and HCl. That presence of, or the difference of one hydrogen is what makes it a conjugate acid-base pair. Something like NH3 and NH4 positive are conjugate acid-base pairs. This is not a conjugate acid-base pair. Ammonium and whatever NH2 is, right? Those are not conjugate acid-base pairs because they differ by two hydrogens. It has to be a single hydrogen. So a buffer solution must contain conjugate acid-base pairs. It doesn't work if it's something like hydronium and hydroxide. So, yeah, these are the equations I recommend you guys know. And so with that being said, we can go ahead and hop back into the rest of my exam review. This is going to be the end of part 1. So stay tuned for the rest.